Welcome to video 16b. The purpose of this video is to offer clarification of points covered in video 16. Also, it is designed to aid you in your completion of group worksheet number 16. Let's begin by taking a look at the Kelly's Cheater method, a method I showed you that you can use to convert repeating decimals back into the fractions that they came from. As you recall, we stated the fact that if it's a one-digit repeater, you simply put that one digit over 9. Noticing here, if we put 9 over 9, we find that 0.9 bar actually has the same mathematical value as the number 1. If we look at this second example and we put 5.9 bar into a form of 5 and 9 over 9, you'll notice 9 over 9 also is the same thing as 1 once again. And if I add 5 and 1 together, I get the fact that 5.9 bar is equal to 6. Now you'll notice that having this 0.9 bar seems to create a very different situation where we end up getting a different number as an answer than what we expected. This is definitely the case you can see here. And what we're going to do is look at this a little bit more carefully. To tackle this problem, I am going to split this different repeating decimal into two pieces. What I'm going to do is put the 0.3 non-repeating part first, and then the 0.09 bar, which is the repeating part, second. Now if I go over here and take a look at this problem, you will note that I can change 0.09 bar into a different format. This different format will be obtained by multiplying this part by the fraction 10 over 10. Now you'll recall if I multiply something by 10 over 10, I'm multiplying it in essence by 1, so I'm not changing its value, I'm just changing its form. So notice what happens when I do this. I would obtain 0.9 bar over 10. So this right here is exactly the same mathematical value as this. Continuing to be a bit creative, I can change the format of this fraction by doing this. I will change it into a multiplication of 1/10 times 0.9 bar. Once again, I will change it to 0.1, which is the same thing as 1/10, and the 0.9 bar, I will use the Kelly's Cheater method to make it 9 over 9. Well, of course, 9 over 9 is exactly the same thing as the number 1, so this simply becomes 0.1. So 0.09 bar turns into the value simply of 0.1. Replacing that back over here, we have 0.3 plus 0.1, and adding those two together, we get the answer 0.4. So if we return back here, notice this value here now becomes simply 0.4. So if we take a look at this very long number with the repeating 9s on the end, we know it's exactly the same as this mathematical value because we can replace the repeating 9s with the 9 bar. And by similar reasoning, we can show that this long decimal becomes this addition because of the fact that this 0.9 bar causes this 1 to be added to that 6 to produce the decimal that you see here. And by the same reasoning, we can show that the decimal 0.256 with a repeating 9 on the end becomes exactly equal to 0.257, because 0.0009 bar is exactly the same as 0.001. And changing this into this addition, we obtain 0.257. Now, why is this important? Well, as a result of these facts, when discussing the use of a decimal such as 0.2569 bar, we are going to avoid using such a decimal with a 0.9 configuration on it, because it means the same thing in this case as 0.257. So 0.2569, a bar just over the 9, is exactly the same thing as 0.257. Placing these two numbers shown above in a list of all uniquely different real numbers would be incorrect, in that the two configurations actually represent the same number. In other words, we would be showing the same number twice. And of course, when we make a list, we don't want to do that. Moving on, I'd like to consider the following. Please take a look at this number. Notice the digit in thousands place is in red. If you look at the number just below it, its thousands place digit is also in red. Obviously, because both of these numbers have different digits in their thousands place, the numbers are definitely not equivalent to each other or equal to each other. Likewise, if we look at this huge number, which probably is irrational, it goes on forever, notice that its digit in this particular place value is a 2. In order to pick a number that is very close to this, but still is not equal to it, all we have to do is make sure that in the digit where this is, this red 2, there is a different digit. And notice we have a red 3 here. So the point is, when we have numbers like these, in order to prove or know that they are different numerical values, they only have to differ in exactly the same digit location. The numbers cannot be the same. And so we know that if these four numbers were contained on a supposed complete list of all the real numbers that could exist, each pair, although very close in value, are indeed not equal to each other and thus represent totally different numbers. One final point. Every real number, whether it be a whole number, integer, rational number expressed as a decimal which terminates or repeats, or an irrational number which goes on forever to infinity without repeating, can be written in a similar ... notation as is explained here. Looking at the integer shown -47, we can easily expand it by placing the decimal point after the 47 and adding zeros to infinity. Still the exact same number. Notice this terminating rational number. It can also be expressed in a ... notation by simply adding zeros after the 6 to infinity. But we show the 3 dots, of course, to show that it goes to infinity. Notice the repeating decimal shown here, the repeating 6. Notice it can be expressed this way to infinity using ... notation. Also, here's an irrational number, and of course this irrational number, starting with 0, 1, 2 zeros and a 1, 3 zeros and a 1, can be shown to go to infinity by expanding it a little bit longer, all right, but still the same idea. So note all of these particular examples very carefully show how we can expand a number out using the ... notation. Perhaps you can recall having seen this game board that we used in our second class this term. This game was called Dodgeball. We took a look at this game and discussed that player 2 could always win. We used X's and O's when you saw the game before. Now we'll instead be using numbers. So let's revisit this game and see exactly how it works. Player 1 goes first and fills in the first row with any numbers they wish. Let's assume all the numbers are decimal numbers after the decimal point, which we shall place here each time. Here's player 1's first play. Now it's player 2's turn. He or she wishes to dodge player 1's move by picking a number for his first square that will guarantee his final number produced in his single row will not match any row of the 6 rows that player 1 fills in. As stated previously, we determined through experimentation and observation that player 2 can always win. All he or she has to do is to dodge the number placed in the first square of player 1's first row. Picking a different number for his first square guarantees player 2 that his final row cannot match the first row of player 1's board because the first digits don't match. Next, player 1 fills in his second or her second row. Player 2 then dodges player 1's second row by placing a digit in his row's second position, different from the one placed in player 1's second row, second position. The game continues with player 2 continuously dodging player 1's moves by continuing the same process. Notice that player 2 has been dodging digits in player 1's choices that are diagonally positioned on his board. And careful observation shows that player 2's row definitely does not match any one of player 1's 6 rows. Georg Cantor, the mathematician that developed this game, realized that by dodging each digit in the diagonal of player 1's choices, one would produce a single row of numbers not found on player 1's board. This theory is known as Cantor's diagonalization theory. Why is this important to us? Well, if we expand this game board so that the player's numbers continue out to infinity, and we assume that every real number is contained on player 1's board, we immediately see that, following the diagonalization theory, player 2 came up with a real number that is not found on player 1's board or list. Therefore, player 1's supposed complete list of real numbers can't be complete. Player 2 has found a number not on 1's list. The number that player 2 has come up with in this particular example is the number M, which you are going to be looking for on group worksheet number 16 by using Cantor's diagonalization theory. So let's tackle group worksheet number 16. In problem 1, I want you to assume that you have a list, or proposed list, of all the real numbers. This list of real numbers is shown in a one-to-one correspondence with the natural numbers. You can see there 1 through 8, down to the nth real number on the list. Using Cantor's diagonalization theory, we wish to find a number M which is not on this supposed complete list. All we need do is construct a diagonal starting at the first decimal place after the decimal point in the first number and continuing on to infinity, dodging each number under the diagonal to produce our members of the number M. So for my first number, first position after the decimal point, I will dodge it and place it in the first position after the decimal point of my number M. Next I go to the second number, second position, and I dodge the second position and place it in my second position of my number M. I next go to the third number, third position, note what's there, dodge it, and place it in my third position of my number M. I go to the fourth number, fourth position, dodge it, place it in the fourth position of my number M. I go to the fifth position of the fifth number. I note what's there, dodge it, and place it in the fifth position of my number M. I go to the sixth number, sixth position, note what is there, dodge it, and put it in the sixth position of my number. Go to the seventh number, seventh position, note what number's there, dodge it, place it in M's seventh position. And in the eighth number, eighth position, I note what's there, dodge it, and put it in my eighth position of my number M. Had I arrived at the nth number on this list, I would go to the nth position and place my dodging number in the nth position of my number M. In question 2, you are asked to state the rule you will use for making the number M that is not on the above list. Before I state the actual rule using the letter N to represent any particular number, let me give a couple of examples. If you look at our diagonal, the number that is listed third, we would go to its third position, and where the 1 is, we would change it to a different number In our case, we changed it to a 5 because the 5 was in the third position of our number m. For example, in the 7th number, we would go to the 7th position after the decimal point, which in this case was a 2. We changed it to a 4. So, how does the rule go? Well, here's what you need to say. In the nth position after the decimal point of the nth number on the list, dodge the digit in that location and place its replacement in the nth position of your new number m. Will the rule you wrote above work on any list? Absolutely. If you use the rule on a different list of real numbers, will the missing number you create always be the same number as you found above? Your number m that you produce will vary depending on what numbers you need to use to dodge various place values found along the diagonal you construct. So is it possible to list all the real numbers? No, it is not. No matter what proposed complete list of real numbers may be presented to you, using the method we have discussed above, you can find a number not on that list. What can we say in conclusion then? The cardinality of the real numbers is greater than the cardinality of the natural numbers. One final question. Find a one-to-one correspondence between the natural numbers and the odd integers. You could do this by just showing that the set of odd integers can be listed. Well, simply relist the odd integers as follows. Thank you very much for watching this video 16b. Hopefully you have found it to be helpful in completing and understanding the material involved in Group Worksheet 16.